exponentials and logarithms, right? So hopefully now we're more comfortable with this idea of what each of those things are, right? An exponential function, right? We can see, right, how these powers, as we increase them, like that result gets larger and larger very quickly. But what does a logarithm help us find? A logarithm helps us find the power required for that result, right? That's what we're going to be looking at today. And we're going to be looking at something like this. 2 to the x equals to 32. Now, back in the beginning, around term 1, we solved things like this using... What did we use? You can use logs, but let's go back to term 1.
You changed the 32 into base 2.
Right, so we were saying, hang on, how can I get these to be similar, right? And we said, hang on, if this is in base 2, if I can get this in base 2, the solution becomes very clear, right? 2 to the x equals to, well, if I make this base 2, that's 2 to the 2 to the 5, sorry. And so therefore x equals to 5, right? Because we're just comparing the power set. Exactly right. Same base, we can equate powers. That's exactly right, Matt. It becomes trickier when we get something like this.
Wow.
What's trickier about this one?
Well, big number.
How are you supposed to know that?
Right, well, first of all, even if we want to try and make things the same base, it relies on the knowledge that we know what this power is going to be. Now, 32 is a relatively small number. What we can use for something like that is we can use trial and error, right? Yeah. Can you use trial and error for this one?
I guess.
It's not a rhetorical question. Can you use trial and error for this one for me?
Yes.
Go. Thank you.
Oh, we're gonna. Do it.
Okay, let's go.
Yeah, why would you already know what it is?
What is it?
Is it 9?
Was it 9?
Second try.
Second try.
He did 6 and then 9.
Do you agree, Harry?
Yes.
Okay.
I agree.
Good. So apparently x equals to 9. There we go. Done. Right. Now, with our new knowledge of logarithms, how can we sort of introduce using them as a tool to solve a problem like this, right, without trial and error? Because we're going to get situations where, hang on, sometimes there won't even be integers, the powers, right? So we need to think about this from another perspective. There's actually 2 ways that we can actually go about solving this. I'm going to give you both of them. So here's method 1. Method 1 says this. Okay. Well, first of all, I don't know what 3 to the power something. I don't know what that's going to be for 19,683, okay? But what I do know is that I know how to rewrite this in logarithmic notation. Right now it's in exponential notation. How can you rewrite this in logarithmic notation?
Right.
Yeah.
Log 3, like base 3.
Log base 3.
And then the big number.
The result, the answer, yes. Okay, so first of all, you have to be comfortable with realizing, okay, when I go from exponential notation, so something to the power of something, and I rewrite it by introducing logs, the base always stays to the base, the result goes into here, and then your exponent becomes on the other side of the equation, which is which is really what logs find, right? They find what the power is required, okay? So you need to be comfortable with that first of all. There's another problem that using this introduces though, right? When I try and put log base 3 of 19,683 on my calculator, when you do that, what's the problem you encounter? Right, you can't actually calculate logs of base 3 on your calculator, right? We don't have that function. What we do have though is... Oh, right, and what is that rule?
Well, if you've got log, well, we have log base 10 on here, right?
Yeah.
So you just put it over log 3, which makes it like base 3 for some reason.
Yeah, and I'll tell you why later on, right? So our change of base law says that, hang on, if I have something in some base, it could be base 3, it can be any other number, right? If I take the log, let's use base 10, right, of our result here, and I put it over the log of that base here, which was 3, you said, Matt, that actually gives me the same calculation. We tried it with values like this. When you put log 32 on log 5, you got, log 32 on log 2, you got 5, right? So over here, if I put this in, what does x equal to? 9, right? Doesn't matter which base I choose for this one, 10 or e. Did it matter?
Yeah.
No, it didn't matter. Like when you put in this log here, you can choose whichever log you want. You can choose log base of 10, you can choose log base of e, it doesn't matter. You can use this as a formulaic approach, okay? The other approach is this. Like I said, there were two approaches, right? The other approach relies on the fact that actually when you're taking logarithms, right? Here, we're introducing logarithms by rewriting it in a different notation, okay? There's another way we can think about logarithms. We can think about logarithms as an operation. In the same way that, when you first start balancing equations, you add some number to both sides, or you square both sides, right? We can actually do the same thing with logs, right? Let me show you how. We start off with the same situation, but this time I'm going to say we take the logs of both sides. And when I do that, something really interesting happens. I'm going to do that, and when I say take the log, right, again, I'm thinking of this as an operation. So I'm going to log whatever I have on this side, and I'm going to log whatever I have over here. That's what I mean by taking the logs of both sides. Right? And again, it doesn't matter what base we're working with. We can work with base 10, base e. Let's stick with base 10 for right now. Okay. And then last lesson, right, you might be wondering, hang on, how does this help us? Well, last lesson we learned some rules with logarithms, right? What was one of those rules that you can see going on here?
Oh, for the power, you can put, yeah.
Right, so think about your index rules, they're kind of similar, right? If I have a power, I can bring it as a coefficient and change it into a multiplication. That's an equivalent expression. So this power, I can bring it down as a coefficient. Okay. And then we actually end up with a similar situation to here because I can do something. I can divide both sides by log of 3. And just remembering that this is actually just a number. That's why we can divide both sides by that, right? So x is equal to log 19,683 divided, yeah, that does look familiar, over log of 3, which is in actuality the same as what we had over here, okay? And x will equal to 9. Jot that down for me. My question to you as you're writing this down, though, is which method do we prefer? One method is rewriting from exponential to log notation. And one is taking the logs of both sides. Those are the two methods we can use to approach a problem like this. Which method do we prefer?
Both.
The first one, why, Harry?
I don't know.
Because you get the same answers in both, but that's just longer.
Okay. Laura says this one's like a lot more working, so why bother? Just do this. Yeah, that's a very fair argument. Okay, do we agree?
Yes.
Of course I'm wrong.
There's no right or wrong answer to this one. Literally, I just asked, which one do you prefer, right? It's not a right or wrong kind of question.
I mean, I guess that's just the way to do it, like, quickie. But that's the way, like, it works.
Which one's the way that it works?
That's just like showing why that one works.
Who likes the quickie one?
I think there's merits in both, right? I think Elora's right with this one. There's a lot, it looks visually a lot less scary, okay? What I do find though is when you're in a test condition, often students seem to make mistakes when they're converting from exponential log notation, like remembering which values go where exactly. Yeah, that's something that sometimes we can make mistakes with. Whereas, taking the logs of both sides, that's an operation you just do, and then you just have to remember your log law, right? So again, there's no right or wrong answer, just whichever you're more comfortable with. You can choose the method that you want for this one, okay? Try that for me. We've got that problem I was talking about before, right? If we wanted to use trial and error, the problem we encounter is if we don't have an integer solution. It's not going to be very easy to trial and error, right? So,
You're crazy, so you can do that trial and error.
so yeah, if you want to, yeah. There'll be a lot of decimals, I can tell you that much. What method, Angus, do you want to use for this one?
Method 2.
Let's use method 2. Okay, let's take the logs of both sides. We're using method 2 here. So I take log of 5 to the x equals to log of 7. I should write my bases. Let's write e. So,
I think I know what.
we've got our logs here. We've got our logs. And what can I do with these either when I've got these here? I can minus.
We'll put the X out.
Okay, yep. So make the x a coefficient. And then, Alora, what's the next step?
And then you divide it.
By,
The log e times.
yeah. So we've got log e 7, log base e 5.
I like method 2 actually. It's kind of,
Why do you like method 2?
well, it's easier. You don't have to do that conversion. Sometimes it's annoying to brain it.
Yeah, I think it's going to be up to you, right? Everyone's more comfortable with different things. If you're fine with this notation, that's fine. Okay. What did you get when you calculate this?
1.20906155.
Okay, when we're writing these out, what I'm going to suggest is, can you give me the decimal places again?
1.20906.
1.20906. So when we're writing these out, I'm always going to encourage you guys to write out whatever's in your calculator display. And then if they don't specify, you can kind of choose the decimal places. We can just do it to 2 decimal places. So you get 1.2
Write out everything.
to 2 dp. Yeah, like just write out a few more than you usually would, just to show the marker, hang on, where have you gotten this rounding from? Just to give us an idea of, okay,
What if they say exact form? Would you write
exact form, right?
log E7?
Then you'd leave it like this. Yeah, that's right. I'm going to ask you to do 2 decimal places for these ones. So.